Morning. I think it's time to perhaps we'll change a little bit topic as well as scale. So we'll, instead of talking on manufacturing on invisible scale, we'll move to more visible scale. So in my presentation, I'll emphasize data aspect of manufacturing, as well as modeling, and talk about sort of future vision of manufacturing. So if you look a little bit at the history of manufacturing, so at least the last 30 years or so, so in 1980s, we have taken really fully flexible human-operated manufacturing system and transformed them into so-called just automated system that we labeled flexible because essentially they were quite inflexible. So what happened is that we have introduced automated material handling systems. So previously, basically machines were standalone, and we have integrated them with robotics as well as automated manufacturing systems. And then over the years, well, a number of acronyms have been sort of invented to label the nature of systems that were evolving. So at one time, we talked about computer-integrated manufacturing systems because we applied more computer power to manufacturing. We talked about also reconfigurable systems as well. Well, the term holonic manufacturing was invented. In some of my colleagues in Japan, they like also biology in manufacturing, so they talk about bionic manufacturing systems. And somewhere along the line, terms such as intelligent and smart have been attached. So let's just talk, probably not too much, but I just have a slide or two about, well, sort of past developments in manufacturing. So it happened that, in 1990, I published a book on intelligent manufacturing, and Tsinghua University decided in 1993 to translate into Chinese. So at the same year, I also initiated Journal of Intelligent Manufacturing Systems. The Journal of Intelligent Manufacturing will actually celebrate its 30 years anniversary next year. So as we see that the interest in intelligent manufacturing, well, began actually years ago. And I could even show some relationship here to Wuhan, because around I think 1995, I met Professor Peigen Li. So he was visiting the United States, and I think a year later, he decided to organize a symposium. As you see, the title of symposium actually has also intelligent manufacturing included. So and so over the years, I have worked with a number of Chinese students, and some of them actually graduated here. So Jack Feng, who you see here as a first author, he actually graduated from Huazhong University of Science and Technology. And so Peigen Li and Jack, we wrote this paper, and obviously also I attended the intelligent manufacturing event that was organized here on campus. I think so the actually writing to the left is old. The picture to the right is new. I have taken it actually, it was taken yesterday. And, this is how I remember the campus, since my visit here in 1995. So this is a signature, basically, I think, of this university. Now, so you see that now we have, second wave of interest in smart manufacturing. I think the first began in also early 1990s, as well as on industrial scale in 1995. So at that year, Japanese industry has decided to launch a large program in intelligent manufacturing. And they have invited partners all over the world. Well, unfortunately, you know, just this collaboration was not necessarily very seamless, you know. So Japanese companies, they have approached a number of US, you know, industries, and some of them, like Boeing, Caterpillar, General Motors, you know, they have joined this consortium. And so in the United States, we have formed so-called program that we named Next Generation Manufacturing System. So Japanese companies were basically visiting US, and within, you know, I have worked very closely with this consortium. In fact, you know, one of the programs that I have led in the Next Generation Manufacturing System Consortium was, you know, actually designing manufacturing of the future. So if I had more time, I could probably, you know, share with you more details how, you know, that vision of future intelligent manufacturing has emerged, well, just basically almost 2 decades ago. So, you know, in the more recent past, so we are now, this is our second revisiting of intelligent manufacturing. We're doing it in different form. I think, so we see now that the initiatives have been taken by individual companies, so corporations have just undertaken many initiatives, as well as regions and countries. So in particular, we have, you know, we will know about the Factories of the Future program, where European Union claims that this is actually the largest program, research program ever initiated in Europe. Now, obviously, in Germany, we have also massive research program, and also obviously here in China. Well, President Obama had a vision, and also he also established a number of manufacturing institutes in the United States. So they are located in different parts of the country, and each of them deals with different aspects of manufacturing. So it happens that I collaborate with one of those institutes. So this is Digital Manufacturing Design and Innovation Institute located in Chicago. Well, it has a very impressive number of members. Essentially, all major US companies are members of this basically industrial consortium, as well as universities across the country. So basically, I would say that the keywords that you could associate with this institute will be digital twin, digital thread, and I think this sort of new basically attribute that we refer to as predictive engineering. So many of the meetings and projects initiated under the institute, they will basically include those keywords. So now, if I was to define characteristics of future manufacturing, so what would they be? Well, and again, I could refer back to the meetings that we have at the Digital Manufacturing Institute in Chicago. Actually, probably one of the most frequently addressed issues is in research is condition monitoring. So companies are interested in actually in predictive engineering, applying the concept of predictive engineering to monitor status of equipment and take advantage of the basically, you know, predicted status, so that production planning and as well as scheduling can be actually linked with the predictive aspect of equipment. Well, you know, some companies in some industrial sectors go as far as maybe going into self-diagnosis or even self-correction and repair. I think this is rather, you know, a goal that perhaps a current practice, but I think there's interest. And also, this is not new. The second bullet here is not new. So we have been always interested in basically increased adaptability and scalability of equipment. And, you know, obviously, the batch size is something that we have been always concerned with, but you know what is different this time, that the batch size it's may vary, you know, significantly. So another one going from batch size of 1 to perhaps thousands or even millions in a very short period of time. So basically the scale has basically changed. So that's what makes difference. And obviously the usual topics such as reduction on the setup time is, again, it has taken new interest, basically with perhaps new models and also new results. Then also now, what you see, no one knows really the future of manufacturing. I think we participate in all in different groups, but it happens that sort of, we still hypothesize. So one of the hypotheses is that really there will be two maybe basic architectures of industrial companies. The first one will be one where you will have physical assets very loosely coupled with the cloud's assets. So basically the digital portion of the enterprise and the physical portion of the enterprise will be really highly separated. Well, today we see this everything as one, everything is run by perhaps enterprise resource and planning system. In the future, it appears that we'll see separability. But on the other hand, we see interest in development of new materials, new processes. Well, this is to serve new products. Well, in such case, this model of a company will be very tightly integrated. So this is the two basically opposite, maybe models of enterprises. And obviously, probably most of enterprises will fall just in between the two models, So they may have elements of this highly integrated and highly basically decoupled elements. What also we see is actually that industries are interested in pursuing programs in new materials, and also including organic materials, because we know all that sooner or later we'll get, basically we'll encounter limits of classical materials, and then we'll have to use also new materials, including organic materials. So, and biology actually is also playing, big role, not only in sort of perhaps the bioprinting, biomanufacturing, but also using concepts of biology to design new materials, as well as incorporate biology in the material themselves. Though integrated manufacturing, has been talked about for decades, but still, many areas in manufacturing are not integrated. One of the examples would be pharmaceutical industries. That in pharmaceutical industry, you may produce powder in one location, and basically pills maybe in another location, in different factory. Okay, so I think time has come to integrate. And then I could use examples of many other industries where actually that integration has not really fully been realized. So this, again, the bio will play significant roles, and if you look at different, small companies or large companies. So all those companies are interested in basically applying biology in order to develop sort of new materials, or as well as processes and methods. So, it almost seems like unimaginable, but that you can use basically maybe dandelions and produce rubber-like material, or you like Ford, you may take agave that probably grows all over the places, and again, you may produce perhaps plastic-like materials that could be used in materials, so to replace classical materials. So as we see that, biology is to play increasing role in manufacturing, both in materials as well as in methods that I'll probably allude a little bit later. So if you want to now differentiate manufacturing of the past to that of the future, so I think I could use here entire alphabet, but I think what is important is basically networking connectivity, that this comes as almost must. I think that's in any model of manufacturing that we discussed, this shows up. Then also, well, the new idea seemed like new idea. Actually, it's not that new. If you look at small industries, this has been actually used for quite a while. Resource sharing, and this is sharing manufacturing resources, you know. At this time, companies compete, so it's difficult for them to imagine that they'll be sharing resources, but actually this is likely to happen. Also, resiliency and sustainability, you know, go hand in hand, you know, that's also important, and because actually of modeling, so we'll see, you know, as what we call greater democratization of manufacturing space. What does it mean? You see, at this time, large companies actually dominate the market, and they largely, you know, engage small businesses, and basically probably are in a position to negotiate contracts that are favorable to them. Well, in the future, you see small companies, because of digitization, will actually increase visibility in the cyberspace. So companies that are located in remote regions will be able to collaborate with companies, again, located elsewhere. And so because of that presence in the cyberspace, I think the companies will have greater visibility, and you know, the actually competition essentially will be more democratic. So, you know, if you look a little bit, you know, sort of step back here on manufacturing, so you see in this lower corner here where we started, so essentially we had, in terms of, you know, connectivity and well, maybe volume of information that was flowing. So initially, probably, you know, there was not much information that was flowing. Also, always like those word of the mouth. I think so. Maybe operator talk to supervisors, managers, and you know, basically paperwork was flowing, and that's how manufacturing functioned. When we moved to manufacturing, automated manufacturing, I think we have introduced computers. So because of that, we have increased computer-machine sort of interaction. That's where the information has taken flow. What we have done here now, so what this digital manufacturing brings is actually machine-to-machine connectivity. So it's probably we talk, you know, there's more talk about it than actually action, but I think, you know, companies are taking serious steps, and actually they see value in increasing this machine-machine connectivity. So, and obviously, you know, this computer-machine connectivity, the vertical connectivity is not going to go away. It's going to also basically stay. So in essence, you know, systems of tomorrow will be much more connected than systems of the past. Here, you see, I like this also maybe a word of caution here, because as engineers, we are usually very enthusiastic, and actually we always like to stay in this corner here. So we see always everything as a rosy picture, and basically see that, you know, how the future is going to be disrupted. But you know, some also perhaps, what if something went wrong with artificial intelligence? Actually, so at least as researchers, we have to pay attention to it. Also, there could be either maybe natural disasters, you know, politics can go wrong too, so different things may happen. And I think, so in essence, what we need to do, we need to think about manufacturing resiliency. Okay, so, and this manufacturing resiliency, I could measure in different metrics. I could use many different dimensions. You know, it applies to assets, you know, basically material handling and transport, supply chain, materials, energy, communications. So because you know, if any of those link fails, then manufacturing could fail. So this is very important, and I don't think that, you know, I have, you know, even listed all of them. I have more exhaustive links of attributes that define resiliency. And then, so in essence, this leads also, I could take almost as far resiliency as sustainability. I could make sustainability really a dimension of resiliency. So basically, we all understand that we'll be moving from linear economy to circular economy, but probably even we should even think ahead in terms of performance economy. So maybe I mean, as you know, that today, customers sort of has profound impact on what's on the market, but I think the time may come that the product developments and changes in manufacturing will be driven more by material and component design rather than basically maybe customer requirements. So this is, as you know, will be moving from maybe linear economy into performance economy. And also, I could even take as far as, because this issue is there, we have also large manufacturing problem that has not been touched. And that's actually the sustainability of the environment, So basically, I don't think that we have paid serious attention, because to this problem. And one way I suggest is that we actually view the bringing back the environment as a business issue rather than, sort of tangential issue and giving it secondary place. Maybe the same as, many businesses approach remanufacturing as very sound business. In fact, if you look at many corporations, so the remanufacturing divisions are more profitable than manufacturing divisions. And one of the reasons is actually cost of materials. So material 20 years ago were probably very low cost. Well, today it's quite expensive. And there's also the other factors. So the same here. I think it's a great business opportunity, especially when in the wave of artificial intelligence, we have all these predictions talking about unemployment. Well, so if we are so this is one of the way, maybe replacing some universal payment system with basically treating sustainability of the basic environment as a business issue. So this is their proposal. Now, so it's basically this probably would happen without just developments in manufacturing. So probably, I mean, but some of it actually it's fueled also by manufacturing. So what is happening is now that that we see these opportunities of new products. You have consumer products. We haven't seen them in the past. Many of the flexible and wearable electronics, as well as home automation. Also, the energy itself is very important. It's sure we are moving from fossil fuel energy generation to renewable generation, but there is no final word on it. I mean, so we don't know exactly. There's probably better solution than solar and wind than we have today. So maybe generation at different scale. We don't have to necessarily follow the old paradigm of mega scale generation, megawatt generation, rather than maybe work on products, on electricity generation that will power our perhaps laptops or our phones. So also energy consumption, that's also another sort of business opportunity for manufacturing. And also those new market. We haven't thought perhaps in the past that maybe manufacturing may actually come to areas such as healthcare. Well, today, probably the best example would be 3D printer, that you can take 3D printer, install in a hospital, and actually then you can manufacture perhaps medication, you can manufacture various supplies, various implants. So that's something that is likely to happen, that in a way factory may come close to the hospital or be within the hospital. And again, I think there's home automation and actually the service industry in general offers great opportunities. So if I was to describe sort of manufacturing of the future, so now it's quite natural that we see increased functionality, and we've seen this for a while. But now when you have new technology, for example, again, additive manufacturing, and we see additive manufacturing equipment paired with classical manufacturing equipment, and just basically which make one unit. So we have just, industry has been doing this in different domains, and I think machine, industry is actually following those trends. And so in addition to, just maybe changing in terms of tools, we'll see also probably different distribution of manufacturing. So, as you know, the manufacturing was like computer systems, was highly centralized, eventually so decentralized, distributed. Now it's to the point that that we have supply chain that, just all over the world. Well, I think so what is going to happen, we'll see now reconfiguration. Some of the supply chains, because of the optimization that will be performed, and of course, and costs such like energy, will be changing. So, and obviously this, we'll still see disruptive technologies, coming, including such as, maybe additive manufacturing. And again, we sometimes ignore scale of this technology, but essentially, we need to pay attention that, that we may have big area additive manufacturing. So, some products that are being printed are larger scales, but on the other hand, other products may be at micro or even lower scale. So, like just in case of biomanufacturing. So, now, perhaps let me just address a little the aspect here, this of basically making use of data in manufacturing, because I don't think there is even, other thought than that of manufacturing being data-driven. So I think that companies has embraced the term big data, and they want to make the best use of it. So therefore, future manufacturing will be data-driven. And now, so how this data-driven approach differs from perhaps what we have learned once at school, or even what we teach today. So basically, data-driven approach it's dramatically different from classical physics approach, because physics approach, and you can sometimes label it manufacturing approach of the past, was basically bottom up. So in essence, if an engineer sees a problem in industry, so she or he will look up for a model that is familiar with, and try to actually basically model the problem, or apply this model the person knows to the application of interest. Now, in data science, this is the opposite. So in data science, we take actually data from multiple domains, and we fuse them into a model. So for the first time, we have opportunity to fuse maybe manufacturing data, with product design data, or even supply chain data. And the data can be both actually quantitative as well as qualitative. You can do even, also basically analysis of text. So we have this great tool now at our disposal that works differently. And this is what has led to the term, digital twin. That basically, if you have data that is sort of rich enough, that describes the phenomena of interest, then you can take data and build, in essence, digital replica of application of interest. So on one hand, you'll have a physical system that will be represented with a, digital model. And we know all that, in manufacturing, experimenting with manufacturing system, no one runs essential experiments in a full-fledged manufacturing. I mean, we do have design of experiments, we run experiments in many areas, but sort of in manufacturing we stay away, except some isolated, basically cases in research institutions. But on manufacturing floor, you don't run experiments. So basically, well, when you develop digital twin, you can run experiments. And you will have this one additional parameter that we have not considered much in the past, actually time, because we can predict events. So we can only not simulate as-is scenarios, but also to-be scenarios. And those can be, basically imaginary, as far as our imagination will take us. So that's a great, and another point of this is actually accuracy, fidelity. That, if you have sufficient data support, that you are truly, you can truly develop replicas. You can develop models that essentially will be almost one-to-one representation, will be very accurate of the physical system. So that's what we are heading with data science. So obviously, I think all these interests here have been inspired by big data. I think that's only basically a term that has been sort of added to existing science of data. And you really, well, at this time, manufacturing really does not have big data. At least very, very selected only maybe branches of manufacturing, like semiconductor industry has quite a bit of data. But, in most of industries, actually, and some process industries, but I think most of industries don't have really big data. They have huge volumes of data that could be measured in terabytes. So almost it seems like, by the sheer size of those databases, they should be big data. No, because often this data is incomplete. Sometimes you have many instances of measurements. So you have, if you imagine a spreadsheet, that in a spreadsheet you have many rows, but very few columns, very few parameters. Sometimes you may have, it's not likely, but in some cases you have maybe many columns, you have many parameters, but not that many instances. So because, we've never designed experiments. We never deliberately collected data. The data was collected for some other purposes that, generation of engineers before us have actually decided to collect. So, and then, for years we have been actually practicing this approach of modeling, that we take data and, we apply basically machine learning, so that's your data science, to develop models, to develop this, what we may call digital replicas of application of interest. And then, there's again new science that we call evolutionary computation that naturally fits this model. Because, once you have developed digital models, so this digital model is different than physics-based model. In physics-based model, most of methods that we apply to solve them are gradient-based. There's also non-gradient optimization, but most of the time we use gradients. Well, the evolution algorithms, they operate on different principles. They don't need gradients. So basically, since these machine learning models are not differentiable, so therefore evolutionary computation is a nice complement to those solutions. So, and then if we had more time, I could actually comment here on the data sources in manufacturing. I think so. These data sources will come by different domains, and basically there's really large variability in terms of data actually availability across those domains. So I have done some writing, basically characterizing, maybe type of data as well as volume and width, and also breadth of data. So in all of this, you see, sometimes we think that if we work on a problem in manufacturing domain, that's it. So we don't look outside. Well, the reality is this, that to practice data science, you need data. So especially us in academic communities, well, we have difficulty actually getting data for two reasons. Sometimes basically such data is not easily available, Well, sometimes, just different intellectual property and in other reasons, competitiveness, leads to difficulty in actually accessing such data. So someone who is interested in basically, starting research in data science domain in manufacturing may look outside. And sometimes there's other domains that you can sort of almost borrow data from to develop your initial prototypes. So the initial, research can be done on data in other domains. For example, someone working on maybe condition monitoring in machine tool industry may look to energy industry, and energy industry is usually much more sophisticated in data collection, so that you can use data in energy industry, develop methods that can be later tested on data in manufacturing once available. Okay, there. Okay, so now, so I think I'm almost, my time is probably getting, I'm running out of time here, so I need to be quick here. So now, so once we have these models, so a question is, basically, well, what algorithms, what methods can we use to develop models, especially if we deal with large data sets, so if we have big data. So I think the research community, has come with the solutions, because, model developments in areas where you have limited data, just have been tailored for those applications. Models that sort of bring large volumes of data, they call for new generation of algorithms. And, basically, because it's natural that if you want to develop algorithm based on large volume of data, well, you need probably, spend more time. That algorithm has to work longer. So in order to reduce this computational time, so research community has offered us so-called extreme learning. So this is, again, basically maybe more, traditional, technology, neural network technology that has been adopted to basically, learning, sort of model building from large scale data. Then also, we have also deep learning that you probably read in various sources. So again, since now we are integrating, we are fusing different domains, so we are taking data across different domains and trying to model those, integrated domains. So therefore, we need, the models are more complex, also more non-linear, and to handle this complexity and non-linearity, well, we have again developed deep learning. So there's a set. So this is a very active area of research. We have a number of researchers actually working in those areas, deep learning, that are to transform the basically those areas. Then again, solving those. So since we are using evolutionary computation approach, and again here there's very specific algorithms that have been developed, again, to deal with those complex nonlinear manufacturing, really twins that just happened. So at this point of time, what I see mostly is just really this islands of digitization. So it will be very difficult to find the companies that sort of is digitized over its entirely business spectrum. Usually we digitize just islands, and basically, so sooner or later those digital islands will have to be integrated. And again, so we need tools for integration these existing islands of models, and then. So I think we could imagine future of manufacturing, and I think there is really different models that could be presented here. I'll only slightly highlight this one that I mentioned before, that this material process product phenomenon emerges, and again this leads to one model. Another model is this of separability of the basically physical and digital layer. And I think the resource sharing would be one that also emerges. And again, you know, it's this resource sharing model has been actually in existence for some time. So if you analyze how small businesses work, so you may come across companies that compete actually with each other, but they share actual resources, because one company may need measuring machine, which is, you know, which it doesn't have, and will use that of competitors. So resource sharing is not subcontracting. It goes much deeper, because it goes into taking over control of the basically manufacturing asset of one company by another company. So this is much deeper concept. And I think in all of this, I would say that this is, you know, we need to innovate. I think so. We all think, and I know it from my sort of research and academic experience, that we all consider ourselves as innovators. I think we are probably usually at best, we somehow end up in this corner. So we might be inventors or creators, but I'm not sure that, you know, I'm sure that we are not really that instantly become innovators. So and the ideas that, you know, that I presented here, they actually call for innovation. And what it happens is that this path from good idea to idea that work in practice is a low really probability path. So it's path that takes basically, you know, just many trials, or we hope that in the future we'll develop a model that will actually, you know, so those trials will be performed, it will be simulated. And so once we have all these basically models, then we'll be able to innovate at much faster rate than what we see today. Because I think this is inherent, that sort of, you know, that path is a very high risk path. And to reduce this path, I think what's needed, you may go back to perhaps Einstein or other researchers, or Edison, you know, and you'll figure out that in order to do this, we need to, so in essence, you know, we need to work differently. We need to become like companies like maybe Uber, Facebook, or Alibaba here, that basically they change, you know, they disrupted market, they change models, because each become large, but yet they don't own any assets, you know. So that's one idea. I don't think that we can replicate this, but, you know, this one of ideas that we can take. We can, in essence, also use, you know, Facebook and Wikipedia, you know, where, you know, basically customers are designing sort of our solutions, our products. So that would be another one. And I think that would be all for today. Thank you.